Okay, good. We move on to to today's lecture. Today is February 20th. Okay, so in optimization, there are two kinds of problems. One is called the unconstrained optimization. The other one is called constrained optimization. Okay, so what would be the general formulation for unconstrained optimization? Very easy. Minimize f of x. No constraint. That's why it's so-called the unconstrained. No constraint. So the solution can be anywhere inside the real space if x is a real number. So any number of x could be a possible solution. We are finding the exact solution, the optimal solution inside the real space. And there could be one that has the smallest function value of f. So the procedure of unconstrained optimization is trying to find the one or maybe more. Maybe there are two solutions that gives same value of f, but at least we try to find one optimal solution x star which gives you the minimal function value f without any constraint. So it's called the unconstrained optimization. But for the constrained optimization, there's a general mathematical format. We can write it down like this. This is a more general one compared to the last one I showed you on Saturday. So from here you can see I introduced one more kind of constraint. This is called the inequality constraint, and this is called equality constraint. So if you have more constraints, just keep on listing those constraints after subject to. So it's like this problem is subject to a list of constraint functions. If you write it down like this way in a in a technical paper, people understand what's going on. You are trying to find an optimal solution x star that will satisfy all the constraint functions that you list, and within this confined criteria, there is one solution that will be giving you the minimum value of f. That is my solution. But I'm only searching for the minimum value of f inside the region that satisfy all the constraints. So give you one example. Minimize x1 minus 2 square plus 6x2 minus 5 square subject to x1 plus x2 equals to 10, x1 minus x2 must be greater than some value, maybe 5. For example, I have a problem like this, and maybe more. x1 must be greater than 1, x2 must be greater than -2. For example, like something like this. I can quickly make a drawing, a figure to indicate the design space and show you how the entire problem looks like. And here's what I'm gonna do, just like what I did last time. So actually there's a center for this ellipse. If you have some sense, this is like the contour of the objective function looks like an ellipse. And the center is located at 2 and 5. So that's actually the center of the ellipse. Okay, and if you trying to find values of, let's use MATLAB. I have MATLAB, right? Oh, I type. So 2 and 5 is right here. 2, 5. So the contour looks like this. Okay. So the contour looks like this. Yeah. Yes. I'm just letting you watch it for watch more. And then when I complete, I will switch back. Okay, so that's the contour, and the red dot is the like a bottom of the ball. If I show you the 3D drawing of this function, it's a function looks like this. There's a bottom. There's a minimum point at the bottom. And the location of that point is basically 2 and 5. Because if you plug in 2 and 5 to this function, you got 0 value. And there's no other point that can give you a function value that is lower than 0. So 0 is the only function value that is the minimum. Okay? So it looks like this. So basically the contour is like making horizontal cuts and then show you different curves that has the same value. Okay, and the red point is the minimum point. This is the minimum point. And when you go away from the minimum point, the function value increases. So if there is no constraint, 2 and 5 is the optimal solution. If this is an unconstrained optimization problem, the optimal solution is 2 and 5. How about if I apply constraints? So let me try to make drawings of those functions. x1 must be greater than 1. It's actually a straight line, a vertical one. And on the left hand side of this red straight line will be infeasible, because over here x1 is smaller than 1. It's infeasible. On the right hand side and also on the line, it will be okay. So on the line, this is x1 equals to 1. It's a part of the feasible space. on the right hand side, x1 is greater than 1. So including the line and its right hand side, that's the place for us to find solutions. So this straight line indicates this particular constraint. Okay, how about the other one? There's a -2. Let me draw a horizontal line. x2 must be greater than -2. So at the bottom, lower than the green line, x2 is smaller than -2. It's invisible. On the line is okay. Above the line is okay. So then, with these two, we already shrink the design space to a smaller area. We already identify some portion of the space to be invisible. But there are two more constraints. We need to identify them. So let me make a drawing of this one. So I need to plug in 2 points and then connect a straight line. But the way I like to do it is like this. -5. And the slope is 2. So it's right here and here. Okay. And it's smaller than. Right. Okay. So smaller than. So that means above this area it's no good. Now our space become even smaller. Only this area would be important for us. Okay, if you know how to draw a straight line. Okay. The tilted straight line is this particular one. But from here you realize there is a equality constraint. That is different. Equality constraint, that means this function must be satisfied. You cannot obey this one. So how does it look like? It's somewhere okay. It's somewhere like this. Okay. Some straight line like that. Okay, and let me try to shrink the entire diagram, entire figure, or move lower. Maybe I move to another page. Okay. It's okay. So this is the equality constraint of x1 plus x2 must be 10. So we must find the solution on this line. So let me, without the line, the design space was this, right? But now with that additional equality constraint, I can only find points on here. So that section, that segment of the on this linear constraint will be the only space for solutions, because we must stay on the constraint, and because of some other inequality constraints, we can only find points right here. So does anyone know where's the solution? If I call this, if I give numbers, if I say this is constraint 1, constraint 2, constraint 3, and constraint 4, and if I label them inside this drawing, this will be my constraint 1, this is my constraint 2, and this is my constraint 3, this is my constraint 4. Can anyone tell me where's the solution? Yeah, the intersection at the cross between what? Exactly. This is the solution. Do you guys know why? We only can find solution on this straight line, right? And we are looking for the location that has the smallest function value. And because of this contour, this is the contour of f, away from the center point, we will get larger values. Closer to the contour center, we have lower values. So this red point basically is the closest point to the center of the contour that, and also stay on this red line. So that is the optimal solution. If you try to use a visualization, like a graphical way to find solutions, you can. Okay? Yeah, go ahead.
I have a question. I mean, in here, in this problem is usually we use a function of mathematics, right? So I mean, mostly the example that we use is mostly two variable, which is surface. Is it always we have to draw it first from the contour and the surface from the three-dimensional space, or maybe if you more than two, I mean, it is difficult to draw inside of the
Right.
dimensional space, and sometimes like this case, not always the intersection is near
Right.
of the lowest contour.
Exactly.
Correct.
Yeah.
So is it so this procedural calculation is not always used in the
Exactly.
surface here. So we can do it as a calculation just more than multi-variables like 3 or 4, something like that.
Yeah. Let me explain more. The reason why I choose two variable problems is because I can easily make a drawing like this, so you can try to understand what's going on. And of course, in real life, there are problems with different numbers of variables. And this is not the, design problems have equations. You may know what it looks like. So making a drawing sometimes help you. However, when the design variables are greater than 2 or 3, it's almost impossible to make a drawing. So sometimes people want to reduce the number of variables. For example, let's say I have 5 variables. Sometimes they just want to visualize it to figure out what's going on. Sometimes they fix 3 of them. Just say, okay, maybe for now, let's fix 3 of them. So I have the other 2. Let's see how these 2 is being arranged inside this design domain. Sometimes people do that. But if you really want to visualize a 5 variable problem, it's impossible. Maybe AI understand, but we cannot see it. And like you said, optimal solution is not always at the intersection. I just came up with this problem just randomly. I didn't prepare this. And in this particular random example, somehow the solution is right there. Yeah. Just it's just very random. Okay, and I'm really happy I made this example because I get to teach you one more terminology in optimization. So can someone tell me, among those 4 constraints, C1 to C4, this one is not important? C3, C3 and C4, yes, but C4 probably is the most unimportant one. The existence of C4 doesn't play any role. So, does everybody understand why? Because if I get rid of it, if I get rid of this one, if I do this, it doesn't change anything. Okay? So this C4 constraint seems like something you can throw away. So in optimization, we say this kind of constraint is inactive. So in the terminology of optimization, if you say active constraint or inactive constraint, inactive means it's not even playing a role. You can throw it away. It doesn't change anything. How about C3? In fact, at this point, it's also inactive because the solution is not affected by C3. So actually, C1 and C2 by themselves can already tell you where the solution is. So for the ones, C1 and C2, they are active constraints. Okay? And there are even methodologies to figure out whether a constraint is active or not in order to reduce the number.
What if the constant of C3 is the above?
Yeah, if that one plays a role, if C3 is placed somewhere else, and it will affect the position of the optimal solution, then C3 is an active constraint. So the definition of activeness basically is defined by whether a constraint is being utilized, is necessary.
I mean the value is the x2 is lower than -2. If we change the value, x2 is bigger than minus I don't know, in the somewhere above.
So for example, C3 is right here, something like this.
Yes.
Then the solution would be right here. No, actually, we don't have a solution because let me see. No, we don't have a solution because if we do that, the design space is like this, but you will violate the equality. So basically, you don't have a well-defined constraint, design space. There's no solution in the design space. Okay. So sometimes we will say if the design space is well defined. So sometimes when we say it's well defined, that means the solution exists. If a space, if we have a, let's say I try to solve a problem, minimize x. The solution is negative infinity. So people don't like to find solution close to the infinity. And sometimes we will say, okay, it's not well bounded. Not well bounded. So we don't want to solve a problem that is not well bounded. We want a well-defined design space. Well-defined design space. There are many ways to describe what a problem looks like, but the problem of optimization is that people sometimes describe things in their own way. So sometimes they use well-defined or well-bounded. You need to read enough to figure out, okay, this means that. Okay, anyway, I hope this helps you to understand the difference between unconstrained optimization and constrained optimization. But for today, we are going to focus on unconstrained optimization, because constrained optimization is much more difficult to solve. So for the first couple weeks, we are focusing on unconstrained optimization. Okay? And today I'm going to introduce a method called Newton's method. And I'm going to start with a 1D approach, basically one dimensional, one variable. Okay? What happened was we usually assume, so for Newton's method, we usually assume an optimal solution exists. So if I give you a function like this, and we are minimizing it, this will goes to negative infinity. If I go on the right hand side, this goes to negative infinity. It doesn't stop. So this is not the problem we are solving, because we usually, for this kind of problem, we will say the solution doesn't exist, because when it reaches to the negative infinity, we cannot define what it is. So we usually try to solve a problem that looks like this, that has a bottom. That's your minimum. Right? So we like problems like that. And in calculus, actually we know over there the slope is 0, right? So the way to find the position with slope equals to 0 is to do derivative. And just to find a position that has first order derivative and equals to 0. We want to find this point. Trying to find this. And what Newton did was, no matter what kind of function it is, let's consider it as let's approximate the function like polynomials. So what we usually do first is to approximate the function as a second order polynomial. What's the method to do that? Something expansion? Anyone knows? Taylor's expansion, yes. So by Taylor's expansion. Okay, so Taylor expansion of f equals to f0. We can say this is the expansion point plus x minus x0 times f prime of x0 plus 1/2 of x minus x0 square f double prime of x0, right? That's Taylor expansion up to the second order. We ignore the high order term. So this is a second order Taylor expansion. So after the approximation, because we're looking for f prime of x equals to 0, so let's try to take first order derivative. So f prime of x would be right? If you take a first order derivative, this term this is a constant value, so this disappear, and this times the f prime is a value disappear, but this part, this is like a coefficient times x. So if you take a derivative, what's left is the coefficient, right? And over here, basically 2 and this 1/2. Basically, you have 2 times 1/2. So basically, the coefficient is 1 at the end. And you keep the term right here and take the coefficient, right? So this is like 1/2 ax minus x0 square. If you take derivative, basically it's ax. Oh, a times x minus x0, right? If you do derivative. Okay? Is it too much? It's calculus. So these are just numbers. Basically, it's like I have a function. It could be in any order. This is a function in some high order, and I have a point. This is x0. I try to figure out what's the function value, and I try to take a derivative. So the slope is f prime of x0, and also I take another derivative. I get second order. Basically, they are numbers, right? So if you would like to, this is like a graphical representation of what's going on. But if you want to, you need numbers to realize this. For example, f equals to 3 sine 2x. So f prime equals to the derivative of this is cosine, so 3 cosine 2x. Because of chain rule, so you have 2 outside, right? If you take another derivative, then you have negative. Did I make a mistake? This is right? So should be like this, right?
Yeah.
You guys make me worry about myself. Okay, so it's like, okay, I have functions like this, and if I plug in a number, for example, if x0 equals to 1/2 of pi, so f prime equals to 3 cosine pi is -1, right? Oops. F double prime of this function, sine pi, no, cosine pi is 0. Oh no, sine pi is 0. So this is 0, something like that. So I have a sine function, and then basically at some expansion point I just evaluate those two values. Okay, and what Newton wants to do is we want this to be 0. We want this to be 0. We want to find a location where this function equals to 0. So with this, let's take a look. Let's rearrange the function. Correct? If I rearrange this, I move f prime to the right hand side with a negative in front of it. Then I divide both sides by f double prime. Then I move x0 to the right hand side. Right, so at the end I get this. Okay? So supposedly, if this function is a second order function, this is how I find the position that is at the bottom. Let's try it, okay? If I have a function f, it has to be second order, then this equation is correct. For example, 6x squared plus 10x minus 20, something like this. F prime is 12x plus 10, f double prime is 12. So if I make a guess, x0 equals to 5, then I try to plug in that function. 5 minus, 12 times 5 plus 10 over 12. So what is this? 5 minus 60, 70 over 12. Too lazy. Calculator. 5 minus 70. Okay. So, and let's make a plot. 6 times, or we can just make a drawing. So right here at the bottom, it's, if I plug in the value, plot if I plug in, just to show you where the position is. Here. You see it's at the bottom. So if the function is a second order function, the second order Taylor expansion of a second order function is itself. And from the from the derivation we know, if I take a first derivative and then make it 0, I get this equation. And this equation tells me if I solve for x, that's the position with f prime equals to 0. Okay? And from here you can tell I made one example that is exactly a second order function. And I chose the first coefficient to be positive, so I'm sure it has a bottom, not going down. And I just basically plug in with a random guess. It's a random expansion point. And at the end, I will get this position. That is the position with minimum function value. And I just prove it to you by a graphical approach. Okay? So how does this help us? With this, we can only find the minimum point of a second order function. But in real life, the function we are trying to find the optimal may not be a second order function, may not be a second order polynomial. So what happened was we can make second order approximations, get the minimum, and then repeat the process again. Make another second order approximation based on the new position, and then get another minimum point. So the procedure of optimization is going to be like this. If I have a function, and if the function looks like this, okay, and with a random guess, for example, this is my random guess, and when I approximate this function with second order polynomial, what I get probably looks like this. Okay, and the minimum of this second order approximation is right here. So I will use it as my new position to approximate the original function again. So for if this is called x1, then on this position, let me exaggerate the function a little bit so you can visualize it more. So let's say the optimal solution of the first round of second order approximation is right there. Then on the second round, I will make another second order Taylor expansion again. Maybe the approximation of the function looks like this. Then this will be my solution for the second round. From there, I will use that point to make a third round of Taylor expansion. I may get something like this. And my solution will be somewhere here. As you can see, I am doing this repeatedly, sequentially, until I'm satisfied. until I cannot find a better one. But how can we do this in a more systematical way? So usually for optimization, we call the following the solution process. Sometimes we call this solution process or optimization process. And this is important because if you are writing an optimization code, the following process will be exactly how you write the code. And for many times in the paper, they don't tell you this. They assume you know how to solve it. Okay, so now I'm going to tell you what the process looks like in a mathematical way. So first, you need to have initial guess. To avoid future confusion, from now on, I'm going to use this, a bracket and a number inside. And I would like to place it at the superscript position. And what is that? That is called the iteration number. So every time we repeat this process, we call this iteration. This repeating process. And we give a number, an index for this iteration. Okay? So you have an initial guess, x0. Then, next step, you need to evaluate f prime of x0 and also f double prime of x0. Evaluate those two numbers. Okay? Next, apply the equation you got from Newton's method. Solve for I'm sorry. I should say k equals to 0 right here. So k is your iteration number. But at the beginning, k equals to 0. So if I do that, I can use k right here. Let me use red color. Here I should say bracket k. Okay, then over here we are solving for k plus 1 equals to xk minus f prime of xk over f double prime of xk. So use the information at xk to get a new point at xk plus 1. And then we do something called the convergence check. So what happens is usually we can draw a box. And here we draw how do you call this? 菱形. I don't know the English. Okay. And if the answer of this check is yes, which means it converged, then your optimal solution equals to the last one you got. If it's not converged yet, so no, not converged yet. Okay? What do? You go back to the top position, and what you need to do is your iteration number advanced by 1. So that's the complete solution process of Newton's method. So inside a computer code, you write a code like this, it will help you to find optima. Okay? And what's the usual way to check convergence? There are two ways of checking convergence. One way is to see if the new solution and the previous solution is already smaller than a very small number. For example, 10 to the negative 3. 10 to the power of negative 3, for example. Or what you can do is you can plug in the function and see if the function value is small enough. And of course, you can also assign a small value. Or you can do both. Or you can, and sometimes, so there are more than two ways. And also, if the iteration number is I should say larger than some limit, you can put an equal, or not no equal. Yeah. If you only allow this process to run for 10 iterations, then when this is over, just stop. Okay? And you can have those criteria being applied at the same time. You can define your own way for convergence check. Okay? So today I'm going to, by the way, if you need to take a rest, you can just go without my permission. I'm not tired, so I will continue. Okay. So let's try to solve for a problem. So keep this in mind. If I'm too fast, we have videos, and later on I will give you this. Yeah, go ahead.
Is this method has a limitation? I mean, or this method is very robust, so it can be applied on any function.
Okay, this method is not Superman. So if a function is in a shape, we call this convex. We call this convex functions. Okay, so usually we call this convex function, and we call this concave function. In Chinese, it's a 2的 and 凹的. Just helping the Taiwanese. Okay, but for English, this is convex, this is concave. So, because we are minimizing, so for minimizing a function, we can only handle convex functions. How about this? If we have two minimum points, then it depends on where is your initial guess. So if you have initial guess right here, at the end you may be located at this position. So we call this local minimum. But overall, this is the true minimum, right? We call this global minimum. So in fact, this method, most of the unconstrained optimization problems that I introduced in the class usually can get local minimum. It doesn't guarantee global. So in our class, I won't give you some crazy problems. I will give you polynomials. So easy. But in real life, it has a lot of limitations. So sometimes people try to avoid local minimum by making multiple initial guess. They want to spread out send out design points in the entire design space, like sending soldiers to everywhere to search for the target. So if you only send out one soldier, you can only get one solution. So there's ways to handle this, is to send out a lot. Let me show you one example in the past. No, it doesn't play anymore. Okay. What's the file name? NL Oh, here. Okay. Okay, good. So what happened was, in the past, I tried to solve this problem. At the background of this design domain, you realize there are linear contours, and the red one represent higher value right here. The blue one represent lower value. So the lowest is at the 0, 0 is at the left lower corner. That's the lowest function value. And there are three constraints: a nonlinear space, and over here there's a region at the center, looks like a twisted triangle. That's the design space. And previously I send out initial guesses in the design space, maybe 400 of them, and I solve them at the same time. And at the time I was trying to see if all 400 solution process can end up with the same optimal solution. So here's the animation. Okay, so that's what happened. in this particular problem, there's only one solution. And the reason why I did this was for a different purpose. But in my earlier explanation of global optimal, like I said, there could be a lot of local minimum. One way to resolve this issue is to send out a lot of initial guesses, solve all the initial problem, solve all the individual problems from each initial guess. At the end, you may end up with multiple points, multiple optimal points. For example, 5 of them. Pick up the best one. So that's one way to find the global minimum. But however, the problem is, if one solution process costs you $10, then 400 times of them cost you $4,000. That's a problem. Or time. If you solve one process, costs you 1 day. 400 processes cost you 400 days. You cannot graduate in time, right? So there's always a drawback of over applying what you are going to do. Okay, thanks for the question. Let's try to solve a problem, real math problems. So if you have papers or iPad, you can try to solve with me. Okay, let's try to solve a real problem together. Let's try to minimize some random. Let's do this. Something like this. I already can see the answer, but let's just solve it in the Newton's way. So let's have an initial guess of, for example, 1. And for the termination criteria, let's say x plus 1 minus xk must be smaller than -3. This is your convergence criteria, or sometimes people say termination criteria. Okay, let's do this. So when k equals, at the beginning k equals to 0, right? And we know x0 equals to 1. And for easier approach, let me derive f prime first. F double prime is 2. Okay, so at the beginning, I need to evaluate those two numbers. F prime at 0 equals to 2 minus 12 is -10. F double prime of 0 is 2. Then x of 1 equals to x of 0 minus f prime of 0, f double prime of 0. So I have 1 minus -10 and 2. So 1 plus 5, that is 6. Then I need to do a convergence check. x1 minus x0, I need to evaluate this value. This would be 6 minus 1, that is 5. It's over 10 to the -3. It's not converged yet. I need to do it again. So I move on to k equals to 1. Just like that. And then my x of k basically is x of 1 now is 6. I need to do it again at 6. F prime of 1 equals to 2 times 6 minus 12, which is 0. I know f double prime of 1 is 2. So x of 2 equals to x of 1 minus f prime of 1, f double prime of 1. So that gives me 6 minus 0 over 2. I got 6 again. And I need to do convergence check. X of 2 minus x of 1. At the end, I have 6 minus 6. That is 0. It's smaller than 10 to the power of 3. Converged. So at the end, my optimal is x of 2. That is 6. That's the solution process. So if I give you an exam, you do it like this, you got 4 points. Yeah, go ahead.
So that just ensures that the optimal solution will satisfy termination criteria, but it's not ensured that that is the best solution.
This ensures it is the optimal because based on how I derive. Remember, at the beginning we mentioned we are assuming all kinds of functions as second order polynomials at the expansion point. We expect multiple approaches will get closer and closer to the minimum. Because we need to stop. We need to stop. So this procedure, let me give you another example, then you will see why we need a termination criteria. But for the other example, let me solve it in MATLAB. I'm becoming lazy. Okay, so now it's programming lecture. Clear CLC, close all is what I always do in the first line. Clear means you clear the design space. CLC means you clear the command window. And close all will close all the figures. So this is how I initiate my code all the time. Now I need to define functions. So there are many ways of defining functions. Let me use handles. So f equals to, let's try to solve 2 times sine of 3x. How about that? And let's try to plot it. Oh, 3 times x. X equals to okay, what happened? There's a way of defining a function by so-called handles. So if you say at bracket some variables inside, and followed by another bracket indicating your function, and the function needs to have the component of the variable. So there's an x right here. So it's very easy to use later on when you plug in numbers. So now then I define another variable. I can define this in a different way. I can call this u. It does the same thing. So to avoid confusion, this handle, this is a way to define functions. So the x right here is just a name. It's not yet a variable. It's a name of the function. But here is a true variable you create inside MATLAB. Right here, this is one way to define a vector, starting from 1 to 10, and the gap between each value is 0.1. So it's gonna be 1, 1.1, 1.2 until 10. I have a vector. And I plug in all the u's and basically all the x. And then the entire vector, I throw it into the f through this handle. So whatever is inside this u, everything will be sent to this f separately. In return, it gets a vector of all the corresponding f values. So by this, you can easily evaluate functions. Okay? Let me see if I can make a derivative. No, I can't. Because if you use this handle, it doesn't do derivative. So should I use a different way? Okay, there's a different way of defining functions. So this is first way of defining functions by so-called handles. Okay, different way. Symbolic. So sims x. Let's use a different x1. So symbolic 2 times sine 3 times x1. So this is a second way of defining functions by symbolic methods. Okay, so if you do this, then f1 is so-called a symbolic variable. So the way to plug in the values is by, let me see, substitute, I think. F1 x1 u. It's running. No? But the first part was right. So up to here it was right. What happened was I made a symbolic function. So first, sims is a way to define symbolic variables. So you can have a variable that doesn't require a value yet. It's a symbol. And then if you define f1 in this way, f1 become a symbolic variable. It doesn't need a specific value yet. Then when I do plotting, the way to assign values to that symbolic function is to substitute. Subs is substitute. Substitute it into this f1 and replacing what's inside, replacing x1 by u. U was the vector from 1 to 10, right? So basically, I'm plotting it, but I'm plotting it in a different way with circles. So that's why I have those circles. But the next part, I think I need to do this. No? Ah, F1, okay. Yes, correct. So with symbolic, you can take derivatives. So DIFF is derivative. So taking derivative of F1 with respect to x1, because the variable was called x1 inside the symbolic function. So let's take a look at df. df basically it will be 6 cosine 3 times x1. MATLAB knows how to do derivative on symbolic functions. So let's do ddf, another round of derivative. So basically second order of derivatives takes another round of. So ddf is your second order derivative. So we get those prepared. Let's start our optimization. So we don't need these. The U and plotting are just for demonstration. So that's common those. I don't need those. And I think I don't need this one as well, because I'm going to use symbolic from now on, because that's easier for me to do derivatives. So at the beginning I need an initial guess. So from now on I'm gonna call my variable capital X. So capital X1 will be my initial guess. Let's say 5. Okay, so this is my initial guess with iteration number k equals to 1. In our notes, we start from 0, but in MATLAB you cannot have index of 0. So in my code it's starting from 1. And iteration number, we can say 1. That's fine. So I'm going to do assign a variable called error. Let me give a large number, 100. While error is larger than 10 to the power of negative 3, we need to iterate. And at the end of iteration, my iteration number increased by 1. Okay, but during the process, my x iter plus 1 equals to x iter minus, I need to plug in df. So substitute into df, and x1 replaced by the current value. Current value is your x iter, divided by substituting in ddf. That's it. Newton's method. So, but during the process, let's try to plot out the process. So at the beginning, maybe I will say display, and I will say initial guess x equals to the value of x1, so number to string x of 1. And during the process, display basically plot out some text information. When here I should say iteration iteration number, some number. So right now I should say number to string iter. Iter is my iteration number. Then I have a comma, and I will just plot out the solution after that iteration. So x becomes number to string this value. I think that's it. Play it. Okay, something wrong. Where? Oh, okay. I need one more small bracket. Yes, I need this. So this is a vector of a string. Yeah, and then I place it into display. Okay, something's wrong. Something's wrong. Oh, I didn't calculate error. I need to update the error. Otherwise, my error is always 100. Error equals to the difference, absolute difference between the new one and the old one. Okay? Run. Done. So initial guess 5, first iteration I get a new value, and then it continues. So what happened? Let's plot out the function to visualize the process. So at the beginning, let me plot the function. Oh, in order to plot the function, I can turn on what we did earlier. The U stuff. I can use this one. But let me plot out, okay, from 1 to 10, that's fine. And maybe we don't need to plot out 1 to 10. Let's plot out from 3 to 6 to narrow the region of our plotting. And then whenever I have a point, I need to plot out that point. So over here I will do a straight line, black, and I think I need to make the thickness of the line thicker. It's a line width 2, and hold on right here. So once I have an initial guess, I can already plot initial guess, and then I plug in here. And then I will plot a circle and red, and keep those. Okay, and whenever I get a new point, I will plot out the position as well. So here I should say iter plus 1. Okay, and the procedure is going to be so fast. Let me make a pause, otherwise you won't see it. Pause 1 second. Okay, let's run the code. Okay, typo, pause. How come it's coming to the top? Something's wrong. Oh yeah. If I have because it always finds the location with slope equals to 0, so it goes to the top. So we have to, so it's not minimizing, it's maximizing. So sine function is not a good function to demonstrate. But if I change the location somewhere here, let's make an initial guess, replace it by 4, a different place, then it will minimize. Okay? If I zoom in, plotting from 3.2 to 4.2. Let's zoom in and take a look. Okay, so it goes this way. And let's try to plot out the second order approximation during the process. Then we can understand why, if we start from here, we will end up with this position. Let's try that. So in order to do that, whenever I get a initial guess, I need to formulate the second order derivative based on that expansion point. So we can do it here. Let me call that TS, Taylor expansion. Why TS? Taylor series. Okay. Yeah, Taylor series. Yeah. Okay. TS, and then I'm going to use. It's going to be a bunch of symbolic functions. Do I use symbolic? Yeah. And then I will place them in a cell. So the largest bracket is cell. So the first cell will be keeping the first function. So the Taylor expansion basically is substituting f1 at your expansion point plus symbolic, so x1 minus your expansion point, capital 1, times the df plus 0.5 times square of this plus ddf. Okay, and then we want to plot out this guy. Plot u, just copy this. But this time we plot out the Taylor expansion. And over here we will change the color. We use dashed lines, red color, line thinner. Let's try this. Something's wrong. Taylor expansion F1. Is it F1? Yes. Initial guess here plus x1 It looks correct. Taylor expansion 1. Multiply. Right here. Thank you. Thank you. Yes. Maybe thicker. So from here, this is our initial guess. And the first second order Taylor expansion gives me this second order approximation. And Newton's method gives you the minimum point of the Taylor expansion. That's why this point was my solution at the beginning, in the first iteration. Let's do it again for the second iteration. Basically, I copy the whole thing to here. But when I get here, I just replace it by ether plus 1. Should be good. Oh, here. Ether plus 1, yes. Ether plus 1. Okay. Did you see how the expansion is getting closer and closer to the shape of the original function? As it's approaching to the optimal, it's getting closer and closer. Okay? I hope that answered your question. This is why we need to do approximation multiple times. Because at the beginning, based on the slope information and the second order information, it doesn't guarantee a good approximation of this shape. It only gives you a different shape. So the solution of that first round of approximation may not be the true solution. You need to repeatedly do it again and again. But to answer your question, in some not well-defined problems or not well-defined spaces, we may end up with solutions that is not minimum. So earlier I chose to initiate with 5, but that's at the region that is not convex. So if I do that, it's not good for me. If I start with 5, I end up with finding the maximum. But the goal is to minimize. Okay, so that's a limitation of Newton's method. The approach gives you some solution, but if the problem was not well defined, you may get an incorrect solution. So as a designer, you need to know what you are solving. And you're just too lazy to solve it by hand. Use a computer to solve it for you. So you at least need some knowledge about the problem that you have. Okay. Very nice. So I will be giving you this code. Maybe I should comment those so you won't be confused. Let me just comment everything. This is a definition of symbolic variable. I need to just plot out the right region. This is a region for plotting. This is a first order derivative of f1. This is second derivative of f1. And then this is plotting f1. Over here, this is to formulate the Taylor expansion. This is to plotting the Taylor expansion. This is a initial iteration number, and this is the initial error value, and this is to display initial guess. This is just to pause for 1 second, and this is basically your convergence criteria. Over here, basically, this is the most important line. This is Newton's method, and this is to plot the new solution, new point. Over here, I formulate the Taylor expansion again. Taylor expansion, and here is to plotting the Taylor expansion, and here is to display the iteration process. Here just to pause for 1 second. Here is to update the error value for convergence check, and here is to advance iteration number by 1. Okay, I will give you this file. So I know for you guys, in order to program like this takes a long time. Don't worry. I get to know how to program this fast with probably experience of how many years? Close to 20 years. When I was a master student in maybe the second year of my master program. When I was undergrad, I took the course of MATLAB. So basically, I only know the basics, and I only know the functions that was taught by the professor, and I know how to do the homework. That's it. But I didn't use MATLAB to do anything else. When I became a master student, I realized sometimes I need to solve problems by computers. I need to plot figures by computers, and that's the moment where I started to use MATLAB to program for my own research. And at the beginning, I couldn't do this programming this fast. And in the last more than 10 years, I have been doing this once in a couple days. When I was a student, probably programming every day, because I was always deriving something, and then I tried to implement it in MATLAB. Okay. So now I can program while teaching. I don't need to program in advance and then show you right at the time. I can just, from the process we can communicate. Like you help a lot, and I hope this procedure help you to understand why we program this. Okay, and also this is related to the course material. So let's try to show a different function. We can change the function right here. For example, if I try to minimize 4 times x 1 to the power of 4 minus 3 times x 1 to the power of 2 plus maybe just a little bit of sine. Just some random equation. Okay, the solution is somewhere else. Okay, so I should plot out the whole thing in a different region. So for example, from -2 to 6. So the real function looks like this. Very flat. Is it really approaching to the true optimal? We don't know. We can zoom in to figure out. This area is so flat. We may not be able to see it if it's a true optimal. Let me plot out a wider region, maybe 10. Oh, so it looks like a bathtub. This function looks like a bathtub. So maybe the true solution should be 0. Because 0 is, here is 0, here is 0. Sine 0 is 0. But we stop at 0.62. That answers your question. Why we stop? Maybe the true solution is 0. Because let's plug in let's also plot out the function value. So during the process, I will display the function value right here. Okay, the way to plot out is right here. Number to string. Okay. Oh, something's wrong. Oh, numeric. Okay, okay. This is a symbolic value. Okay. So as you can see, the function value is dropping. And the difference between the 8th and the 7th iteration are so small. It cannot reach even, it cannot find a smaller difference. I should say it cannot find a larger difference. If we iterate one more step, the difference is smaller than the requirement. So it won't approach. So if I make the criteria even smaller, if I drop it to 10 to the power of -6, it will iterate more. It's taking too much time. Let me turn off the pause. We don't need a pause anymore. It's faster. Now, it only advanced by one more iteration. Let's also plot out the error to figure out what's going on. So the error was already 10 to the power of negative 11. It's very small error. So Newton's method has to stop there. But if we plug in, is it truly the smallest value? I question myself. If I plug in a different value, let's see what's going on. If I substitute by 0, see? If I plug in 0, the function actually has a smaller value of 0. But the problem is this function when it's close to the bottom is so flat. The slope is so flat. It's like you're sliding from the, how do you call the slide in the garden, in the kindergarten, in the playground when you slide. When you slide, at some point you just stop. So Newton's method has this kind of limit. When the slope is so small, it doesn't slide anymore. But truly, the solution should be 0. That's a problem. So when the slope is too small, you cannot go further. If I try to enlarge the error once more, if I say 10 to the power of 30, let's see how many iterations you will go. Bless you. One more iteration. So numerically, computer believes there's no error. Previous step and the current step. Let me just confirm one thing. If I just do this. Oh. Yeah, it's even smaller. You can truly get smaller values if you plug in a smaller value. But the slope is so flat, numerically it doesn't go further. So that's also an issue in optimization. If the function has a very flat bottom within the entire area, we call this gradient approach. The method that we're using are called the gradient approach. This is so Newton's method is so-called a gradient approach. So it relies on the gradient of the function. And there are some other functions that is completely different from gradient approach. Those methods can overcome this issue. So there are non-gradient approach methods, and we will talk about them in the future. Okay? What time is it? So in the next lecture, I would like to introduce second order Newton's method and even greater order. So maybe do I talk about it today? Are you guys okay? Is it too much for today? Because the next week I will be in Australia. So if I For next, am I in Australia, or is it next week is a holiday? Oh, next week is a holiday. Okay, so you won't miss anything. Maybe I can talk a little bit about higher order. Is it too much? I feel okay. I feel fine. I didn't drink water. I didn't go to bathroom. I was talking all the time. I was coding. I was using my brain. I feel okay. Okay, maybe a little bit. And if it's too much, I will stop. Okay, so that was earlier we were doing one-dimensional. Now we move on to multi-dimensional. So basically we are minimizing a function with multiple variables. So variable, we have a lot of variables and they are placed in a function. And followed by what we did earlier, we can do Taylor expansion again. So again, we do a second order Taylor expansion. This will be like this. So it's getting crazier. Okay. This is called a gradient. And this is called a Hessian matrix. Gradient vector. So what's inside the gradient vector? Let me write it down for you. Partial derivative. So it's like you're doing partial derivatives, and then you plug in your expansion point. Okay? Does anyone know Einstein's notation? Really? Okay, very good. So you know this? Okay. That's good. So let me say something about Einstein's notation. The Einstein, okay, real Albert Einstein. Okay. Why do we need Einstein notation? Because Einstein did a lot of mathematical derivations, right? And there were way too many. He decided to invent a new notation to avoid a lot of handwriting. So he decided to describe math in a certain simplified way, and we have to follow it. We need to know what he's writing, right? Okay, what happened was, whenever there's summation, he decided not to write down the summation. So in everybody's mind, this is a usual summation. Okay, we have ci times xi. We have a summation of a symbol. But in Newton's mind, from here, I know it's a summation. So he can derive more equations without writing the summation sign. Okay. So let me tell you why this could be helpful. Because there are people writing papers in this way. They just say the above equation was written in Einstein notation. They assume you understand what's going on. To fool people, okay? To make people feel like they are fool. Who did that? I did that. Just to make your own paper fancier. Yeah. Let me show you. Somewhere I mentioned Einstein. Let me see. Let's see. Where the Einstein notation is used. So this is Einstein notation. So some people write papers to make it look more complicated. So you won't be able to understand too easily, and they will judge your paper as a higher ranked paper, more valuable. Okay, that's a trick. Okay, now go back to here. Why did I mention that? Because if you want, you can write a gradient into different forms, right? A vector could be like summation of partial f partial xi, plug in x0, I from 1 to n, but you need unit normal vectors. So ei. Do you know what is ei? So e1, e2, e3, you may not be familiar with. How about ijk? You guys know ijk, right? Basically, they are like this. So they are sometimes called normal basis. Basis vector. In here, basically, you have normal basis vector in a size of n, a longer one. So this is like so basically ei equals to 0 or 1. So when I equals to how do I write it? No, I should not say it. It's not like this. EI is too fundamental, cannot define anymore. So it's like this. So this is the ith component. Yeah, like this. EI is like this, and the length is n. Okay? So you can write it in this way, and for Einstein, he would like to write it in this way. He just ignored this guy. This was ignored. So when you see a notation I and I together, then it means summation. So this is in Einstein notation. Okay? Yeah.
How can we know that number of terms is in or is k?
Oh.
How can we-
Okay. So usually, when you derive a general equation, the derivation should be general enough it suits for any number of components. So when he wrote in this way, he doesn't care about the number of components inside the summation. So this derivation can be applied to any dimension. Yeah. So it's good for you to do derivation. Okay. Later on, if we write in this way, it's going to help us to derive. Okay. There's another guy called Hessian matrix, right? I will tell you what is Hessian matrix. Hessian matrix, basically, it's a huge matrix that includes all the second order partial derivatives. It includes all the second order partial derivatives, and if you plug them in, it's going to be like this. If you plug them in, it's going to be like this. This is a n by n matrix. Okay. So how do we write it down in a matrix form? It requires two summations. Okay. So, have you ever seen this? Placing two normal bases together. Have you seen this? No? So have you ever seen this? E1, E2? No? Yes? It's indicating the position if it's a 2 by 2 matrix, right? So here is like a 1 1, here is 1 2, here is 2 1, here is 2 2, right? So E1 E2 is like indicating the position over here, 1 and 2. So this is like 0. It's like this. It's like a unit basic matrix. Okay? So there's a name of it. I forget what's the English name of it. Let me find it. Hydroid? Oh. This. Here. So IJK basically is E1, E2, E3. II is this guy. IJ is this guy. So if I write E1, E1, if it's a 3 by 3 matrix, only the first one is 1. E1, E2 is this guy. Okay, it's called the dyadics. Every time I write a paper, I forget. I need to Google for it. Okay. You can Google for this, then you will know. Dyadics. I don't even know the Chinese name of it. Because I don't like to write papers in Chinese. So I don't sometimes memorize the Chinese name of it. Okay? So for Newton it's easier. So this is a pair of same index representing one summation sign, and the other pair of same index representing another set of summation. So for Einstein, it's like this. Okay. So there's something about dot product. If you understand what's going on, A could be written as summation of AI, EI, right? I from E to N. And it can be written as AI, EI. B could be written as BJ, EJ. J can go from 1 to N as well. Then it can be shortened as BJ, EJ. Okay? And if you do dot product, A dot B, it can be written as AIEI dot BJEJ. And these two are scalars. The rest are actually they are tensor notations. So for scalars, you can change its position. They're just multiplying a number. But for tensors, you cannot swap its location. So this actually can be written as AIBJ, then EI dot EJ. So Bj was being moved to the front. So what is Ei dot Ej? There's something called Kronecker delta. Kronecker delta. By the way, this is graduate course. You should learn something in graduate level. Kronecker delta. What is Kronecker delta? Kronecker delta. Here. Kronecker delta. Oh, sometimes people like to write, or you can also write it in this way, Ij. The same thing. Kronecker delta equals to 0 if I is not j, equals to 1 if I equals to j. Okay, Kronecker delta. So let me go back to where? Here. Kronecker delta. I just copy it. Okay? So what's happening is this guy becomes Aibj Kronecker delta. And what's interesting about Kronecker delta is it can swap the index. So if there's a, for example, there's a j right here, they're the same. You can use this I to replace j. So at the end, it becomes Aibi. And Aibi is written in Newton's notation. If you recover it back to its origin, it's a notation from I to n, Aibi. Basically, it's A1, B1 plus A2, B2, plus A and Bn. That's dot product, isn't it? And did you find how powerful Newton's notation is? Not Newton's notation, Einstein's notation. With Einstein notation, you can derive algebra more effectively. So for dot product, initially we have this, and we return the whole thing into this, right? And then we replace something into Kronecker delta, and then we can quickly derive this is actually Aibi. So without memorizing how a dot product should be done, you can already derive its Aibi. And Aibi at the end is exactly how the dot product should be done. Okay, so the reason why I show you this is because we have some dot product right here. In the Taylor expansion, we have some dot product. So I want you to be able to figure out what's happening later on. Okay. Yeah, go ahead.
So it means that the reciprocal calculation in the platform is change from the factor to the product and then go back to the Taylor series.
You mean right here?
Yeah, I mean
Go down.
yes, I mean this.
Which part?
Yes. Wait. Yeah.
Here, dot product. Okay.
Okay. So it means the function of the I change from the factor into the product and then substitute again into the Taylor series, because the Taylor series expression is it contains a factor.
Okay. What Kronecker delta did was um, it helps you to figure out whether that delta needs to be 0 or 1.
Yeah,
So this has to be proven. This has to be proven. But I didn't prove it. I just tell you EI dot EJ equals to Kronecker delta IJ. I didn't prove it. But it could be easily proved by just listing all the possible derivations, and then you'll realize, oh, you're right. Kronecker delta truly is this, and EI dot EJ truly is this. They are the same. So I'm not going to prove it, because proving it is very straightforward. Just plotting out, listing out some possible combinations, and then you will find the sequence. So the purpose of using Kronecker delta here is to replace the EI dot EJ in the formulation to simplify it. So you don't need to deal with the dot product sign and also those vectors. Let's take a look at.
So, Professor,
Yeah, go
what is
ahead.
the difference between dyadics and Kronecker delta? So is it same?
Say again.
So what is the difference in between dyadics and the Kronecker delta? Because before that you mentioned that is the dyadics. EI
Da-
dot EJ.
EI dot EJ at the
Both are same, dyadics and
Uh,
Kronecker delta.
EI dot EJ will equals to Kronecker delta IJ. If you maybe we can try it. Let's say I have three by one vectors. Okay, so E1 is going to be like this. E2 is going to be like this. E3 is this. So we are proving EI dot EJ equals to Kronecker delta IJ. So how do we prove it? So we can try E1 dot E1. So we have this dot. So at the end we have 1. So in this case, I equals to J. You can continue to list all the I equals to J cases. They all equals to 1. But for E1 dot E2, it's gonna be 0. So this is the case for I won't be the same as J. So when you list out everything, you just prove it. And by definition, Kronecker delta IJ, it basically shows you either whether it's 0 or 1, and so it's like a simplified symbol to represent 0 or 1. So Kronecker delta 1 is 1, Kronecker 2 is 1, Kronecker 1 2 is 0. So it's easy to just replace EI dot EJ by Kronecker delta IJ. I don't know who invented this. I feel like there's a magic behind it. Whoever invented this is so magical. But since it works, we just follow how. So I cannot tell you how come a person come up with this idea. I don't know. But I know how to use it. Okay? And if you want to prove why this is working, why you can swap the index, you can also try to prove it by yourself. If you want, you can try to prove this part. Okay, you can try it. You will realize, oh yes, this is true. Okay, the reason why we do this is because maybe someday we want to do this. How do we do this? So it's going to be AI EI dot H. We don't use the same index. We need to use different index. I J K, so E J E K. Excuse me. Okay, and then dot B I J K L E L. We have to do this. So like I said, we can put all the scalars together and then put all the vectors to the back, but we don't try to change its orientation. Okay? And what's interesting is that this is actually Kronecker delta Ij. This is actually Kronecker delta KL. And what's going on is there's a J right here. I can swap this. I can swap to I. And there's a K here. There's a K here. I can swap this by L. So at the end, it's going to be AI HILBL. So what is this? It's two summations. AIHILBL. I from 1 to n, L from 1 to n. Have you ever seen someone solve for general equation of A dot H dot B so effectively? Because in the past, what you need to do was you need to truly do matrix multiplication. A is a vector, A1 to AN, dot, H is a matrix, 1, 1, 1, 2, dot, B1 to Bn, right? And in the past, what you need to do is to transpose this one, multiplying entire H and multiplying entire B. And you need to truly do multiplication. And you ends up with a lot of terms summing together. Even you complete that, you don't even know whether there's a general equation for that. At the end, this is the general equation. So in computer, if you want to write down how to calculate A dot H dot B, write this, that will so effectively gives you the final answer. I bet there are already computers doing this. You just don't know. So there's an advantage if you have something like this. And why do we talk about A dot H dot B? Because we have a vector right here, a matrix right here, and a vector right here. And when we try to derive equations with vectors and matrices with dot products, sometimes Einstein notation will help you. It may not directly help you today or in the following weeks, because later on I will just tell you the answer. But I can tell you it helped me when I try to derive a method in my own research. Okay, if there's time, I will try to tell you. I think this is enough for today. This is already a lot. I didn't thought I will tell you Einstein notation today. But the first course I learned about Einstein notation was a course called Continuum. Continuum basically is the elastic mechanics of materials. So in the course, in the first day, my advisor asks us, the lecturer asks us, who has heard of tensor? Some people raise their hand. Tensor. 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 So that professor asked us, who has heard of tensor? Some people raised their hand, some people didn't. And the professor said, whatever you learned in the past about tensor, it probably was wrong. So from today, I'm gonna teach you what is true about tensor. And he probably spent 3 or 4 weeks introducing the Einstein notation, A dot B, B dot A, and how do we do derivatives, and how do we do cross product. I'm not covering everything. I'm just covering dot products only. If you are interested in the future, you can try to find some supporting material to teach yourself about tensor. If you are in the field of solid mechanics, tensor is important, because there are so many books that are written in tensor notations. See, there are so many stress in different multiple index. So see, I'm not lying. Einstein notation, right? So when I took optimization, my lecturer about optimization actually didn't spend time on tensor, but after several years of teaching and using it, I realized sometimes you may need it. That's why today I introduce you the Einstein notation and some derivations. I hope that that helps. Okay, that's it for today. And who missed the attendance check? Where was it?